Hi, good day everyone. My name is Alex. Thank you so much for taking the time to attend our webinar today. I am Leader's National Trainer, and today we're going to be taking a look at Ubiquiti's channel optimization techniques, which is a topic that we discuss at length in our Ubiquiti certified training as well. Today is just a quick 30-minute session. Questions are most welcome as always. And as always as well, you are welcome to send through any topics or suggestions to webinars@leadersystems.com.au in order for us to improve our training and to present content that is relevant to you. Just a quick note on this webinar that there are some flashing images which may be disturbing to people that are sensitive to that, so just a quick note on that. Today is not product focused at all. We're going to dive straight into the technical side of this, and we're going to look at, as a first starting point, what channel selection means in terms of how it can impact your real world throughput. So this is a real world environment. I've got a Apple TV up and running here, and what we can see as the receive rate and the transmit rate there is 960 megabit per second and 720 megabit per second respectively. So quite a good upload and download rate. And what I'm going to do now is I'm just going to hop onto this UDR. I'm going to hop onto a channel that I know is interference prone. So I'm going to hop onto channel 44 there, which is a non-DFS channel. And I'm just going to scroll down to see what tools Ubiquiti make available to us to see the interference in a specific environment. So the first one that we're seeing here is in the 2.4 gigahertz space. Obviously, we all know that the 2.4 gigahertz space is quite saturated, and you can see this in our test here as well. You can see the transmit retry rate is quite high, so about 30%, and our received retry at this point is 0. I don't think there's much happening on the channel at the moment, um, and we can see how busy that environment really is. If I go forward slightly, you'll also see that it's not just the 2.4 gigahertz space. The 5 gigahertz space can be quite densely populated as well. It really depends on what your neighbors have set up around you. So you can see there, for example, there is a fair amount of noise and interference on that channel. Ubiquiti have given us tools to identify which channel we should be operating in. And in our example here, we are seeing channel 1, 6, and 11, and we can see the radio frequency that we're operating in, the specific channel, and the utilization of that channel as well. And we can see at what point the interference is at. So minus 76 for channel 1, 6, and 11, which is quite interference prone. If I go to a broader channel, so for 40 megahertz, for example, you'll see that there's still a ton of interference on there. You can see the scale at the bottom as well to see how that's represented. If I go to the 5 gigahertz space, obviously because we have a lot more channels available, there's not as much interference, but there is still some interference here on the 40 and 80 megahertz wide channels. So some of these you'll see do actually have a fair chunk of interference on them. And I'm going to get to one here in a second, like this one. You can see the interference is actually at minus 55 dBm, which means that channel is pretty much completely unusable. So this is built into the Ubiquiti interface. It's really easy for us to identify which channels we shouldn't be using. So from this, I can very clearly go, channel 36, 40, 44, and 48 are not to be used. I can see that the channels next to them are fairly open. I can use those instead. I can also see that if I use 160 megahertz wide channel, I would be quite interference prone. So I can see the channels 106 and the channel next to that as well is quite clear. And essentially that's what I should be operating in. Because I've changed the channel, I've not changed anything else, I've just changed the channel. I can see that there's a reduction to my transmit rate already. So this was much higher before. It's now only 640 megabit per second. It's about 400 megabit per second lower. If I refresh the page, you'll see it goes down even lower. It takes a second for this to update correctly, but you'll see the RX rate and the TX rate goes down massively. So it's a big consideration in terms of selecting the correct channel. Obviously, it's something that has a big impact, and we now understand that this is something that should be checked. One thing I will note here as well is that we didn't apply any other changes. So we didn't change the output power, we didn't change the frequency, nothing. So it's still got the same modulation, etc. It's purely by selecting the incorrect channel that we've had such a reduction in throughput. So we do a quick analysis here to compare the two. We can see before and after the impact that this has had. So 960 versus 648. Those are physical data rates. They're not the TCP throughput rate. But it is pretty representative of how much you can expect in terms of the amount of data throughput that you will lose. In real world, what we typically see is that you will see whatever the physical indicated rate is on screen, you'll typically get about half of that in TCP real world throughput. So if we lost 400 megabits per second, we know in real TCP throughput we lost 200 megabits per second just by selecting the incorrect channel. And this isn't an isolated scenario. This is a very common scenario that we see every single day. So let's take a look at how the wireless protocol actually works. So this is the 802.11 protocol, and this is the protocol that is still in use by all of our client devices today. So when I say client device, I mean laptops, cell phones, etc. And essentially, this is the primary way that your client device communicates with an access point. So to start off with, we have our access points and our laptop as shown on screen. What your device will do, your client device, it will essentially do what they call a clear channel assessment, CCA. So it will essentially turn the laptop into listen only mode, and it will listen for any RF around it. So in our example here, it's listened. It's analyzed that there's no other competing devices in the environment right now. Nothing's chatting to the access point. And as a result of that, it will start communicating. If we have another client device in our environment, and essentially they want to speak with the access point as well, they'll do the same thing. They'll do a clear channel assessment. And in our environment now, it would pick up that another client device is currently transmitting to this access point. As a result of that, it will say, perfectly fine, I cannot start transmission right now. What I'm going to do instead is apply a random back off period. So typically this can be a couple of milliseconds or a couple of nanoseconds. It's really fast. And essentially it's going to say I should try this again in a certain period of time. So I should try again in our example here in 2 milliseconds. So it's backed off, and essentially it's just turned the device into listen only mode again. What happens in the interim is that my transmission finishes on my other device, and my device 2 at this point will again do a clear channel analysis. Go, okay, perfectly fine. I need to do a try again. It will do the CCA, scan the environment. It's found that nothing is interfering at the moment, and essentially it's going to start broadcasting straight away. So that is still how all of your client devices work, and we can understand how tightly we need to control this as well, especially in environments where you have this happening very frequently, such as environments with um, lots of client devices. So lots of access points, lots of client devices, so lots of cell phones, laptops, etc. It really needs to handle this very quickly in terms of the timing. This gets tighter and tighter the more client devices you have. Just an important note, what we saw previously in terms of how quickly it decides which channel, or sorry, when to start transmission, that happens extremely fast in the real world. It's nanoseconds or milliseconds. So it's not as latent as I'm showing it on the screen. So let's take a look at how many channels there are available in the 2.4 gigahertz range as a start. So we'll keep referencing the 2.4 gigahertz space in much of these slides, just due to how limited that frequency range is. In 2.4 gigahertz, we only have 3 non-overlapping channels, and those channels essentially range between 2412 megahertz and 2462 megahertz. Each one of these channels can at a minimum be 20 megahertz wide and at a maximum be 40 megahertz wide. And this is only in the 2.4 gigahertz space. In the 5 gigahertz space, we can have bigger channels. So that means a access point with its channel set to 1 would essentially have a 20 megahertz wide channel where the center frequency is at 2412 megahertz, and then you would have pretty much 10 megahertz on each side of that. So what you would have or end up having is a channel that ranges from 2402 megahertz all the way up to 2422 megahertz, so 20 megahertz wide channel. So in the 2.4 gigahertz range, we only have 3 non-overlapping channels, like I said before, and those channels are labeled as channel 1, 6, and 11. When we refer to these channel numbers, we're always just referring to a specific frequency. I can hear you asking already, why do we only use such a small part of the spectrum? I mean, if we know that we can transmit vast amount of data, why don't we just use much larger channels? The reason for that is it comes down to what governments around the world have granted us. In most of the world, channels 1 to at least 14 is available. Or at most 14, sorry, not at least. And essentially that would mean we have this limited allocated spectrum. It's an ISM band, industry, scientific, and medical band, and it's pretty universal. You can find the same thing in most countries. Um, that being said, the reason why we only have so little space available is because that's what government has allotted to it, and it's because of what is next to it in terms of the spectrum that it's using. A lot of governments and military institutions and hospitals and um, pretty much any type of service you can think of would have allocated space already. It could either be for telecommunication or it could be for um, any type of electronics, etc. It really comes down to what has been adopted in your country and when. In Australia, it's primarily just these three channels that, or this specific frequency range that is available. You can go up to channel 12, if I'm not mistaken, 12 or 13. But this is what they've made available to us in the 2.4 gigahertz space. Um, it's not the only channels that we are allowed to operate in. We can operate in the 5 gigahertz range, and recently we can actually start operating in the 6 gigahertz range as well. So one of the reasons they're so restrictive with the space or the amount of size spectrum that we have available is because of the way that your wireless propagates. Lower frequencies will always travel further, and as a result of that, it's much more restrictive in the 2.4 gigahertz space. There are simply not enough frequency ranges that do not overlap, and as a result of this, it's one of the reasons we've implemented and have started using the 5 gigahertz space. Due to its limited spectrum availability, we can also have our maximum channel size go up to 40 megahertz, where in the 5 gigahertz space we can actually make that a lot bigger. So taking a look at our channel availability again, generally speaking, we need to have a gap between the channels that we use. So in our example here, this would be channel 1, 6, and that would be 11. As a good rule of thumb, we generally recommend having a 5 megahertz gap between at 20 megahertz wide channels, and then doubling the size of the gap every time the channel size doubles. So for example, if I go from a 20 megahertz wide channel to a 40 megahertz wide channel, I would need to increase the size of my gap by at least double that. So if I went from 20 to 40, I would go from a 5 megahertz gap to a 10 megahertz gap. And if I went from 40 to 80, I would go from a 10 megahertz gap to a 20 megahertz gap. It's just best practice to avoid interference. I'm going to show you why that is in a second as well. So this is a perfect space where all of our equipment's operating exactly as it should. There's no overlap in terms of the channels, and everything just works. In the real world, what you'll often have is more like this, where you have overlap between channels 1 and 3. Someone has placed a access point on channel 3. This could be your neighbor, this could be an incorrect placement of your own access point. Really, it depends on what your environment is. So this will show us exactly why we see a decrease in throughput and an increase in latency if we don't leave a gap between the channels and if we don't select the correct channels. So knowing that a clear channel assessment is performed first, if we had a client device and an access point that overlapped into our channel, what we'd see happen is this. So essentially my client devices here on the left-hand side are doing what they're supposed to. They talk, listening and then talking to the access point, doing that clear channel assessment. But if I had client devices on channel 3, because it overlaps and is directly overlapping into the channel that we use, it would do this clear channel assessment and it would go, okay, someone's already using this spectrum, so I can't communicate right now. And this could be from a completely different access point. It could be from a neighbor, it could be from anywhere. It could be from an access point that's hundreds of meters away. If it's in the same channel, it essentially means there is potential for this to constantly go, I can't do anything right now because that channel is already used by somebody else and it picks it up as noise. So this is what we see in the real world, and this is what we're trying to avoid by selecting the correct channels. So as I said earlier, we need to leave a gap between the channels that we use. One of the reasons for this is what we call the tail ends. It's also referred to as adjacent channel interference. And what you'll see is when that 20 megahertz wave gets generated, it's not a perfectly clear electromagnetic wave. It's not the wave itself, it's more just the space that it consumes. And you typically have what you call tail ends that come off of that as well. So you'll see here that it actually spreads out, the RF energy spreads out towards the side. And it can actually overlap into channels that are next to it. So for example, if my sensor frequency was at 5,580, it would overlap all the way up to 5,550, even though my channel width is only 20 megahertz wide. That's why I need to leave a gap between this access point and that access point and the channels that we select. So really important that we get this right. So we understand the impact of selecting the wrong channel, but what about channel sizes? There's a couple of considerations here. The ability to change channels or to change the size of that channel is called channel flexing. And in modern Wi-Fi, we can choose between 20, 40, 80, or even 160 megahertz wide channels. I didn't show 160 megahertz wide channel on the slide today, but essentially what applies to this applies to the rest of it as well. With Wi-Fi 7, we are also introducing even larger channels. We can potentially go up to 320 megahertz wide. So people tend to think that going for the largest channel is always best. However, the best recommendation is actually to start small and move up as needed. Smaller channels have a bunch of benefits. So first and most surprising is that smaller channels, generally speaking, can actually increase range. So if I make this 20 megahertz wide, for example, it can actually increase the range of my access point. This is something that people often overlook. Uh, People tend to think that it's not much because every time we half our channel size, you tend to gain 3 decibels in your signal to noise ratio. Humans are pretty bad at understanding or interpreting the decibels generally, but in a nutshell, every 3 decibels is double the potential range. So if we're going from an 80 megahertz wide channel to a 40 megahertz wide channel, it's potentially double the range. And again, same thing for 40 to 20 megahertz. What you're going to see in a real world is not a just a linear scale like that, where you have suddenly double the range as you go from 40 to a 20 megahertz wide channel. It will be a percentage, so it'll be let's say a 30% increase in range as a percentage value, as opposed to just being double. But the potential for it to increase range is double. So smaller channels travel further, but they also increase the number of total channels you have available as well, which is important for high density deployments because it means you can have a lot more access points with 20 megahertz wide channels than you can with 80 megahertz wide channels as an example. We're going to see an example of this in a second as well. The one big benefit of having a broader channel, and this is inescapable, is that larger channels are capable of transmitting more data. And think of this as a highway. This is the easiest analogy I can come up with. The broader we make our highway, the more cars we can have on it. Same thing applies to our RF spectrum. If we have a 20 megahertz channel, it's a pretty narrow highway. If we have a 80 megahertz wide channel, it means we can have more cars on that highway. So larger channels increase throughput, although there is a point of diminishing return. Especially in the 160 megahertz range, oftentimes you'll have to test the environment that you're in, and you'll see that going for a smaller channel might actually yield higher TCP throughput rates, even though the indicated physical rate in the interface is higher. So this is something you have to test. There's no finite rule for this, but generally speaking, I would say between 40 and 80 megahertz wide is recommended for most business deployments. If you have a really dense environment where you have tons of access points and tons of client devices, 20 megahertz is perfectly fine. So it depends on what your throughput requirements are as well. So if we know we don't need more than, I would say, about 10 to 15 megabit per second, it's perfectly fine to go for 20 megahertz wide channel because that would be supported. It would support that data rate on that smaller channel. It means it's much more resilient. It's much less prone to interference, um, although the throughput is, generally speaking, a bit lower. So let's look at an example of large channel sizes. This is the problem with using large channel sizes. One of the biggest things is that you have much more potential for interference from other access points. So let's say this is your broad 80 megahertz wide channel, and you've set it up on a specific frequency range. These are your competing access points. These are neighbors. And you can see how a 20 megahertz channel or 40 megahertz or another 20 megahertz wide channel can potentially interfere with yours because your channel is so broad. If I were to set this to a 20 megahertz wide channel and just use this piece of the spectrum, I would mitigate all of this interference and I would potentially have a higher throughput rate even though my channel is smaller. So let's take a look at the 5 gigahertz spectrum availability. So the 5 gigahertz frequency range is broader, and generally speaking, more channels are better. It means we can have more non-overlapping access points. So in the 5 gigahertz space, we can actually have up to 25 20 megahertz channels that do not overlap. Or, of course, we can do larger channels as well. This is a pretty good way to represent it. You can see here the number of channels that we have available in certain spaces. And if we increase the channel size, obviously it decreases the total number of channels that we have available. So I can have 25 non-overlapping 20 megahertz channels, or if I go all the way up to the extreme of 160 megahertz wide, I can see that I can only have 2 non-overlapping channels. So this is an important consideration. We also see a little bit less tighter control around EIRP limitations in the 5 gigahertz space due to the shorter distances traveled by the electromagnetic waves. So larger channels obviously mean throughput, and smaller channels mean less overlap. That's the idea behind it. And that's why we have the 5 gigahertz spectrum available, because it's much broader and allows us much more space to go beyond 3 access points in a small deployment or a large deployment. So part of the 5 gigahertz spectrum is part of the DFS range, and essentially DFS relates to the channels you can select. There's no option to disable DFS. So what DFS is, it checks for radar signatures that operate in the 5 gigahertz space. If DFS detects radar, essentially it says it turns the access points into listen-only mode for a period, and it stops transmission, and then it tries to move to a new channel. So on this new channel, it will scan for radar again, and if it still picks up radar, it will move again, and it will continue on like this until it gets to a clear channel. So the idea behind this is that you would not have your access points cause interference with radar systems. So one of the things you'll note is that a lot of the consumer access points will not make use of DFS channels. So the channels in red here are non-DFS channels. And generally speaking, when you buy a consumer brand, you'll see that the channels available on that equipment is only this range and this range. It's only in really in enterprise equipment such as Ubiquiti where we see the availability of this. There are some exceptions to this, but generally speaking, this is what you'll see. So there's a quick question that I have here for you. How many of you have actually purchased a consumer access point on the box? It says 160 megahertz wide in terms of channel support, channel width support. But when you install it and you set the region to Australia, the maximum that allows you to go up to is 80 megahertz. This is due to that DFS selection. So what you see in a lot of the consumer electronics is they need to support a specific power control method. It's called TPC. And that TPC essentially says if it's in a DFS space and it picks up radar, then it should perform the actions to avoid that. It can be costly for consumer brands to try and implement this. And as a result of that, all they do is they go, we can't operate outside of that frequency range. So what we're going to do is we'll limit the maximum channel size to 80 megahertz because that's all it has available. You have to use DFS channels if you are looking to do 160 megahertz wide. So I also know that a lot of people think I'm not close to the airport, so why would I really be concerned about radar? It's generally not the airport radar that we're concerned about. We need to take a look at weather radar. That's the big point of concern. I have a lame joke here for you guys, a dad joke. So the other day I was walking down the street and I saw a dome that looked like Doppler radar. As it turned out, it was just a Doppler ganger. I'm sorry, that's the lamest joke about radar. Um, but anyway, so what we really need to think about is how weather radar spreads out. Um, you tend to think I don't live close to weather radar, so why would it impact me? Ubiquiti actually lists the weather radar, uh, generally the ones that are known, on the Ubiquiti. Uh, uh, that's the UISP Design Center tool, which is available free of charge for you to use. And you can see here that one of them is listed close to Adelaide. It's in the Selix Hill. And we can see that the important one here is the range. This thing goes for 474 kilometers. And you can see the frequency that it operates in as well. So 5,625 megahertz. And if I were to go one back, you'll see that that is smack bang in the middle of our DFS range. So that is what we are trying to avoid. And if we know this goes for 474 kilometers from this point, we are damn sure that it's going to stretch across the entire Adelaide. And this isn't just in metropoles, it is in regional areas as well. You'd actually be surprised how many there are. Just to give you an example of how broad this actually spreads out, I did a quick Google Earth um, analysis of how far this radar stretches. So I'm literally just going to continue zooming out until we hit the fringes of this radar. So the radar is on the little yellow dot there. And as I'm zooming out, you can see the entire Adelaide would be covered by that radar. We haven't hit the fringes of this radar yet, and we're going to start hitting it in a second. So the red line is the outline of how far that weather radar actually stretches. So it's a massive area that it covers, and potentially all of those spaces are subject to DFS events or detecting radar. So it's a massive area if we start looking at a map. And then this reveals it. So we tend to think, because I'm in regional Australia, I'm not going to pick up DFS events. There's radar throughout the entire country. So, and again, these things stretch for hundreds of kilometers. So yes, DFS is a real consideration. And in certain scenarios, it would mean that you are not capable of using those DFS channels. A good question that I frequently get about this is if we understand that these DFS channels are prone to interference, why do we use them in the first place? The reason for this is if we were to eliminate them, we would only have a very small amount of channels available that we could actually operate in, and we wouldn't support 160 megahertz wide channels, which would mean we lose pretty much all of the benefits of Wi-Fi 6. So we do have to use DFS, and there's no way to really mitigate this. We are fortunate in indoor environments that we have these big cages around us that protect us from radar, and it mitigates a lot of that interference, but it does still come up a lot. It's something that we see frequently from the comments in training as well. I'm actually getting a few messages coming through right now where people are saying I'm picking up DFS on one of my clients. So yeah, absolutely, that's something that will happen, and there's no neat way around it. If you have a lot of DFS events, then you will end up using the non-DFS channels in order to get away from that. So we've also alluded to the 6 gigahertz spectrum earlier as well. So Wi-Fi 6E is now available in Australia, and specifically the 6 gigahertz band, and only the lower portion of the 6 gigahertz band. So we're waiting on Ubiquiti to release the firmware that supports this, and it's only on the U6 enterprises that this would be potentially supported. But what is the benefit of the 6 gigahertz wireless space? So think of having a 6 gigahertz space similar to having a completely different 5 gigahertz space. In other words, we again have, in our example here, we have 25 non-overlapping 20 megahertz wide channels, and we have potentially 3 160 megahertz wide channels that do not overlap with each other. So The reason we're implementing the 6 gigahertz range is because we need to have more channels available in order to avoid overlap and in order to increase our throughput. Um, this is very new. You're going to only see really adoption of this within the next year or two as consumer devices start to catch up to this and access points as well. So this spectrum is made available above essentially where the 5 gigahertz range ends. And the idea behind this is it allows us to have a space that is interference free for the moment. As more people start to use it, of course, we're going to have the same thing that happened with 5 gigahertz, where we just see more and more people starting to adopt it. Right now, it's interference free. We've tested it in the office, and we've actually reached gigabit per second speeds for the first time on wireless, which is extremely impressive. Again, we're waiting on Ubiquiti to release that firmware that makes it available to us in Australia, and we've actually followed up with them recently to try and get this. So, for the first time ever, we'll see real world TCP throughput rates that are in excess of a gigabit per second on our wireless access points, which is incredibly important and impressive as well. So one thing to note as well is that the U6 Enterprise has a 2.5 gig Ethernet port. Obviously, if we're breaching 1 gigabit per second on wireless, we need to offload that into our network somehow, and that's why it has a 2.5 gig Ethernet port. So what's most impressive to me about 6 gigahertz, the spectrum, and the U6 Enterprise is that it can do 2.4, 5 gig, and 6 gig at the same time. So it's essentially like having 3 access points that are all serving clients at the same time. So it improves the density of your environment massively. Again, at its very minimum, I can have potentially 3 20 megahertz wide channels on one on 2.4, one on 5 gig, and one on 6 gig, and they can serve clients individually. All what I can do is I can have two 160 megahertz wide channels and one 40 megahertz wide channel to serve my client devices. So it's a massive improvement, and I highly recommend checking out equipment like the U6 Enterprise in order to really benefit from this. We also like I said before, we're only using the lower part of the spectrum currently. The upper part of the 6 gigahertz range, in other words, above 6,425 megahertz, is in consideration all the way up to 7 gigahertz, although it is not yet available in Australia and it's just due to regulation. This will eventually likely become available as Wi-Fi 7 comes around. With Wi-Fi 7, we'll see 320 megahertz wide channels, so we do need this space available. So let's talk about output power. The best recommendation we have here is that lower output powers are generally speaking better. The first impact of high output power is that you have, or that you're potentially causing and receiving much more interference. By increasing the output power, we are increasing the range of our access points, but it also potentially means we are now allowing our APs to be detected and be competing with other access points and equipment. So this is our example where I have competing access points and I'm set up myself on channel 1 by increasing my channel size, oh sorry, not my channel size, my output power. I can see that just by that one action, I've now made my access points into a possible cause for interference in the other access points. And it means my access points now also pick up the client devices from those access points as well, which means I am getting more interference, which means again, if that clear channel assessment happens, that I am going to pick up a lot more interference from client devices that are not directly connected to my access points. We don't really go into depth about this today, but basically beacon and probe frame mechanisms drive device discovery, and this can have a big impact on your network as well. So by increasing output power, we are increasing the amount of coverage that we do, but it means we have much more client devices that are probing our access point, which wastes airtime. So the recommendation is to always use the smallest output power possible and scale that up to match the real coverage that you need. I always say the best coverage you can have is where the wireless cuts as soon as you leave the premises. So if you leave your home or if you leave your business, the wireless should be cut to your device because it means you don't get interference from competing in-band access points. One thing that I'm going to do here quickly as well is I'm just going to go to Unify's Design Center. I've drawn up a map, just a fictitious building, and I've mapped out all the walls and I've added access points into the space. I've matched the wall types. I've even gone as far as adding the network cable in. And what I'm going to do is I'm going to take out one of these access points. I've even added the switches, as you can see there. I'm going to take out one of the access points and I want to show you how much interference we potentially get from access points if we select the incorrect channels. So I'm going to move this one out and you can see that the access points that are in the different rooms, so that access point and that access point, as I'm indicating now, they are stretching into the lounge that I was trying to cover with the access point I had previously. So if I had those two access points on the same channel as the one in the lounge, it would essentially mean I have direct overlap and I have direct interference from the other access points as well. So we need to figure out the best way to space this so that we know we're going to have overlap in terms of coverage, but we don't want overlap in terms of channels. This problem gets exasperated every time we reduce the frequency as well. So if I go to 2.4 gigahertz, for example, which I'm about to do, you'll see that the problem becomes much worse. And the amount of coverage that we get from the access points actually increases massively because lower frequencies travel further. And if I even move these access points all the way up to the edges, you'll see that they still provide a huge amount of coverage and potentially a huge amount of interference as well. So how do we select the best channels? Believe it or not, and some of you might chuckle at this, but one of the common scenarios that I still see every single time we do training is that people tend to deploy access points like this, where they go access point 1 is channel 1, access point 2 is channel 2, 3, 3, 4, 4, 5, 5, etc. So this is probably one of the worst case scenarios. The only way you could make this worse is if you made everything the same channel. But essentially, this does not allow adequate gap or space between the channels like we've seen before when we were talking about channel sizes. So this is a strict no-no. I do not recommend this method as you will have a ton of overlap. You'll have a ton of client devices competing with each other the whole time. Another thing that I've seen is people know that channel 1 and channel 11 don't interfere with each other. So what they're doing is they're taking all the access points and just sticking them on channel 1 and 11. So in the example here, we can see that, okay, those two access points don't interfere with each other, but channel 1 here and channel 1 here does interfere with each other. So this is very commonplace in the real world. My apartment where I live is very reminiscent of this, where the consumer electronics that everyone uses is just everything stuck on channel 1 or channel 11. And what you end up having is a ton of interference, and no one's using the 6 gigahertz space as an example. Or you can find the inverse where everyone's using the channel 6, and it's super prone to interference as well. So this again, strict no-no, don't recommend this setup. Let's take a look at a correct setup, or the best term for this would be a meh setup. So what this is I've got my channel 1 selected, that's fine. Channel 6, perfect. Got channel 11, so 3 non-overlapping channels. And I've tried to space out channel 1 from channel 1 as far as I can on this map, so this access point doesn't interfere with that access point. But there's an exception here. Channel 11 is within range of this channel, and sometimes there's no way to get around this. It means there is going to be a level of overlap in this environment. So it doesn't quite get the pass, it gets a frowny face from my side, but this is very common in the 2.4 gigahertz space, where we don't have enough channels available in order to have an environment that is completely non-overlapping. So no real way to get past this. That is why we are generally recommending to only use 2.4 gigahertz for your IoT devices at this point. Most of our consumer electronics support the 5 gigahertz space. Highly recommend using that for your faster devices instead. Let's take a look at the correct setup. So this would be set up on 5 gigahertz. We are using channel 36, 149, 52, 100, and 128. And again, I'm spacing channels that are relatively close to each other. I'm spacing out as far apart from each other as I can. And this one basically gets the pass mark from us, as it's a good way to deploy your channels. If you want to map your channels, it's a very good idea to use Ubiquiti's Design Center, the Unified Design Center. It's an awesome tool for this. It allows you to graphically represent a space. All you need from the customer is essentially a floor plan, or you can even download floor planners as an app that you run on your mobile device, and you can map spaces to generate a 3D map like this. So that's a pretty good way to do it. And one thing we also need to talk about is the nightly channel optimization or auto channel selection versus manual channel selection. So you have an option in the UDMs and the UDRs where you have a feature called nightly channel optimization, like it's circled in the red. What that does is it switches the access points that are associated to it into a listen-only mode for a brief period of time at a predefined interval in the evening. So I think it's around 3 o'clock in the morning. It will turn the access points into listen-only mode. And based on the amount of interference that it picks up from competing access points, it will see that channel 1 and 6 are in use, and it will try to then go, okay, channel 1 and 6 are in use, so I'm instead going to use channel 11. And we'll do this every single day in order to move the access point to the channel that is least occupied. This isn't a faultless system, and we generally recommend to actually do a manual setup instead. So our example here with 36, 52, etc. Is actually the recommendation from Ubiquiti as well. The reason for this is that we have a lot more granular control over the channels, whereas with nightly channel optimization, it will hop to whatever it thinks is best. And you could potentially run into a scenario where it chose channel 1 during the course of the evening because it didn't pick up any noise at that time. But at 8 o'clock in the morning, the business fires up next door and the channel becomes extremely densely populated. So our recommendation is to rather select your own channels and base it on what we have available from the Ubiquiti interfaces. So really that's pretty much it for our channel optimization best practices. This is only a very surface level overview of this. If you want to get any more in depth on this, we do go into a lot of depth about this in our training. Ubiquiti's certified training is available throughout pretty much the entire country as per the dates listed on screen. Highly recommend checking it out. We spend a day and a half talking about channel optimization and how you would boot off bad clients, etc. So a really, really in-depth training on this, and we generally see resellers living from this and changing complete network setups in order to improve their client devices. So dates available. Do encourage you guys to check it out. We also have all of the Ubiquiti webinars coming up, so the ones listed on screen right now. Please do feel free to register for any of the webinars coming up, and remember there's exciting prizes for every time you attain one of these things, and you go into the running to win access points and routers, etc., etc. So highly recommend checking it out. If you want to register for any of the upcoming webinars or to attend the training, please feel free to have a look at leaderacademy.com.au. With that said, we're going to break now into the Q&A session.